let's move to the work done within isothermal processes. Work done on the gas, as we know, going to be area under the curve, okay, on PV diagram. Since this is a curve of hyperbola, so we have to use integration of, okay, the P, the function, to the respect of the volume changes in, okay, from initial state to final state, integrate the P to the respect of the dV. Negative here because we want to calculate work done on. As we know, previously, work done on is equivalent to negative P delta V. Alright, so our P here, since we're talking about ideal gas law, the P can be substituted with the equation of states, right? Where we have P equivalent to nRT, PV equivalent to nRT. So only P means that nRT over V. So as we know, nRT are constant. So we can factorize nRT outside or in front. Okay, so the one we are going to integrate is actually dV 1 over V to the respect of V. Okay, so since this is a hyperbola curve, so the product of this will be negative nRT ln V, where V here, okay, is from initial to final state. Okay, so if we want to have positive of equation, we can manipulate this one, okay, so we can have in terms of this pattern. When we have change V initial over V final, then the negative sign will be vanish, isn't it? So this is still work done on the gas by isothermal process. If let's say the question asking for work done by, as we know, work done by equivalent to negative of work done on. Therefore, work done by is negative nRT ln V initial over V final. For this case, work done on, okay, negative nRT ln actually V final over V initial. So for isobaric processes, represented by horizontal line on PV diagram, its experience changes in terms of volume from initial state to final state, as well as temperature, initial temperature, final temperature. However, it remains at the one value or remain the same at the same pressure here. So technically how to make the system to have pressure constant, okay, where we can set the piston is freely movable. Therefore, any kind of changes experienced by the system, okay, can move the piston upward or downward freely. In terms of work done on the gas, okay, as we know, it's equivalent to negative P delta V, or it means that area under the graph, right? So in terms of first law of thermodynamics, delta E internal equivalent to Q plus W on. So now we can have negative P delta V here. Right. Now isovolumetric processes. Isovolumetric processor, it means that volume remain the same throughout the process. Another name of it is isochoric. Okay, how to make volume remain the same? Technically, we can clamp the piston so that it cannot move, right? So we remain the same volume. In terms of PV diagram, the same volume means that it's represented by vertical line on PV diagram, because it's only on the same volume of the container. It experiences changes in pressure from initial state to final state, as well as temperature. The only one constant is volume. Whenever volume constant, based on for work done, okay, for work done on the gas, based on this P delta V, whenever there is no changes in volume, so the work done will be 0. Work done on the gas will be 0. So our first law, delta E internal equivalent to Q plus W on, for this part is 0. That is why we have delta E internal equivalent to Q only. Okay, this is specifically for isovolumetric processes or isochoric we call it. Next one will be adiabatic processes. Okay, for adiabatic processes, this is a special process whereby there is no exchange of heat between the system and the surrounding. Okay, technically, we are going to do the process very fast, very rapid, or we can have insulation. Okay, therefore, there is no Q will be transferred in or out from the system of our gas. So the condition for adiabatic is actually Q equivalent to 0. Therefore, our first law of thermodynamics, delta E internal equivalent to Q plus W on. So the Q is 0 because the process is done very rapidly or thermally insulated. Okay, so there is no Q transfer in or out from the system. So at the end of the day, we are going to have delta E internal is equivalent to work done on the gas. Okay, this is special for adiabatic process. In terms of PV diagram, actually for adiabatic it's also a curve. For PV diagram, okay, it's also a curve. However, okay, seems like similar, right, to the isotherm. Okay, so how to differentiate between these and the isothermal process? Okay, so recall back that isothermal happen at the same temperature. That is a keyword. Adiabatic processes may experience changes in terms of temperature, even though it's also hyperbola or curve like this. Quick quiz 19.4. Okay, characterize the path in the figure as isochoric, isovolumetric, isothermal, or adiabatic. Okay. There is hint given here for path B, Q equivalent to 0. The blue curves are isotherms, okay, or it gives you information of the temperature. So this quick quiz gonna be your assignment, your task, right? After you've finish watching this video, please submit your answer, write down your answer in the Google Classroom. So now example 19.5, an isothermal expansion. One mole sample of an ideal gas is kept at 0.0 degrees Celsius during an expansion from 3 liter to 10 liters. Okay, this is the isotherms of it, right? How much work is done on the gas during the expansion? So we know that the formula of work done on is equivalent to nRT ln V initial over V final, right? Just substitute everything. The R is 8.31 joule per mole dot Kelvin. Therefore, your T must be in Kelvin, right? Must be in Kelvin, so that the unit of K, Kelvin here, cancel out with the unit Kelvin here, right? Ln, okay, for ln, You don't have to change the unit of V initial and V final in terms of meter cube because they are going to cancel each other. Right? So you have here negative 2.7 times 10 to the power of 3 joules. Okay, this is the amount of work done on the gas. This one should be on the gas. Part B, how much energy transfer by heat occurs between the gas and its surrounding in this process. So we are going to use thermodynamic first law, delta E internal equivalent to Q plus W. But as we know, isothermal, it means that the T remain the same. If the T remain the same, delta E is equivalent to 0. This is the condition. We are going to explore more on this, okay, within chapter 20. Right. So as of now, when we have isothermal, it means that T remain the same. It means that delta E internal is 0. Therefore, we are left with this only. So our Q will be equivalent to negative of work done on. Right? So negative of negative 2.7 times 10 to the power of 3 joules. That is why we have positive amount here. Okay. C. If the gas is returned to the original volume by means of an isobaric process, okay, how much work is done on the gas? So for isobaric, the formula of work done on is equivalent to negative P delta V. And our P here is an RT initial over V initial. Okay, so substitute all the values of N equivalent to 1 mole. R is 8.31. The T is 273 mass in Kelvin because to cancel out the unit of the R in per Kelvin. Right, and then divided by the V initial. It must be in meter cube now. You have to convert it in terms of meter cube now, right? And then times with the V final minus V initial. Okay, so also must be in meter cube. From liter, you need to convert it into meter cube. So you have 1.6 times 10 to the power of 3 joules. Okay, of work done on when we return the process by isobaric means. So, boiling water, example 19.6. Suppose 1 gram of water vaporizes isobarically at atmospheric pressure, which is this is the atmospheric pressure. Its volume in the liquid state, V initial equivalent to V liquid, which is 1 centimeter cube. And its volume in the vapor state, okay, V final, which is V vapor, is equivalent to 1671 centimeter cube. Find the work done in the expansion and the change in the internal energy of the system, ignoring any mixing of the steam and the surrounding air. We completely refer this as ideal case. Imagine that the system simply pushes the surrounding air out of the way. So, work done is equivalent to, work done on is equivalent to negative P delta V. You have negative 169 joule of work done on. And then the Q involved because it involves phase changes because it's vaporization process. So Q equivalent to delta M LV. So we have mass of the steam here and the V. So substitute the mass of the steam and the LV of steam. Right? You may get this info from table. Refer to your textbook. So you get here 2260 joule of Q. If it is positive, it means that it's transferred into the system. If the Q is negative, it means that the Q is taken out, okay, from the system. So based on thermodynamic first law, thermodynamic first law, delta E internal equivalent to Q plus W on. Okay, it's going to be 2260 plus negative 169. You have 2.09 kilojoule of changes, increment. Because this is positive, it means that increase, the delta E internal is increased by this amount, right? Next one, okay, example 19.7. A 1 kilogram bar of copper is heated at atmospheric pressure so that its temperature increases from 20 degrees Celsius to 50 degrees Celsius. A. What is the work done on the copper bar by the surrounding atmosphere? So work done on is equivalent to negative P delta V, but since this is talking about copper bar, so delta V here going to be in terms of bulk modulus, changes in volume due to the expansion. So we have for delta V, this is a recall, delta V is equivalent to beta V initial delta T, right? So we have substitution of delta V here, right? And we know that beta is 3 times of alpha with the condition beta is equivalent to 3 times of alpha. What is alpha? It's coefficient of linear expansion. Why is it 3 times? Because volume experience changes in 3 dimensions. That is why we times with 3. Okay, V initial delta T. So you have things that can be rearranged. Okay, because this is a constant, so 3 alpha we put it in front, right? And then the volume initial is figured out by using density, okay, where we know that density is equivalent to mass over volume. If we want to have volume, it's mass over density of the substance. So substitute that value or this information for volume initial, okay, times delta T. Then substitute the rest of the information in terms of the figures, right? You will have, this one can be in terms of Celsius. No need to put it in terms of Kelvin. How to know? Because your alpha here. Your alpha here, the unit is per degree Celsius. Therefore, your delta T may, you may put it in terms of degree Celsius. So it cancels out the unit here. So you have this amount of work done on the bar of copper.